Okay. Okay. Looks like we're recording. All right. So we're ready to start looking at module number 2. Module number 2 is going to be looking at resultants of concurrent force systems. Okay. This is just the very beginning of statics. We're going to start looking at vectors and forces and resultants, as you can see here. And where we're going to focus our time and energy is going to be in a lot of I think 3 sections in chapter 2, not chapter 2 in its entirety, but we're going to be looking at 3 sections in chapter 2. So what I do is I have down here the places that we're going to be looking, and then also the sample problems and the concept application problems that we're going to be doing. These problems right here are your practice problems, okay? So you'll notice that once we get through our lecture, you're going to be handing in practice problems and application problems. And if we go back to module 2 and we look at the 2 assignments you're handing in, practice problems, as you know, are the ones that we're doing in their entirety in class. I do have a PDF here for you to open up, and they list those very same sample and concept application problems, as you can see here. Okay, so these are going to be the ones that we do. So again, we're going to be getting these through the lecture, the work that we do here, and then those are going to prepare you for the application problems, as you see. And these are going to be worth 10 points each. So it looks like there must be 11 problems because I think it's a total of 110 points. So what I do here is I will give you the problem number, the page that they're on. In this book, I don't know, you can like it or not like it, but what they do is how they structure is they'll explain some concepts, do some examples, and then they'll give you problems that relate to that. And those problems are the ones that we see here on the application problems. They are kind of scattered after each one of those sections. So there's not like end of chapter list of problems. They're in areas. That way, what's nice about the way that they have it laid out is if you have a problem in a section, you know that the pages immediately before it would have dealt with that. So you don't have to try to hunt through the chapter for examples. Additionally, I always give you the final answer. This way, as you're working independently, you know if you ended up with the right answer or not, and you can kind of have confidence moving on. You still have to show all the work. You still have to show the whole process, but this way you at least can know, okay, I'm good. I can go on to the next one, okay? Rather than hoping for the best when you hand something in. And my expectation is you're kind of checking those final answers before you hand in, and you're asking questions in class or independent work time during our Zoom time on Fridays when things aren't coming out to the final answer. That's what I'm expecting you to do, okay? So that's why it's important to be working these kind of as we go along, at least trying some of them so you get some practice, and then making sure that you feel confident and know what I'm asking for, okay? So we'll go back and review those when we get ready for that. So I'm going to go back to our learning plan here. Now, I do have a PowerPoint presentation that's here that will pull up. It's in PDF format. And it's just going to kind of walk us through the sections and the illustrations that are there. And I'll kind of go back and forth between under my camera and looking at our PDF here. You don't have to print off the practice problems, the application problems, or the PowerPoints, okay? Unless you want to. If you want to have a hard copy of them, you can. But when you hand the things into me, you just want to make sure that everything is included and then that you have the problems appropriately labeled so that I know which problems are what, okay? So I won't be handing the application problems and the practice problem sheets out just because it's just a list of problems that are already on the computer. The reason I did it for module 1 was because those were the problems you were handing in. So I wanted you didn't have the textbook to go to, okay? All right, so this is chapter 2. Now, if you wanted to, you certainly may follow along in the textbook. This is going to be, should have showed you that, and I know you guys have looked at it already. It's going to be in the McGraw-Hill Connect little link here. And then when you get there, there should be something that says, go to Connect section, and then down on the right-hand side is going to be the ebook that you can launch, okay? We talked about that last time, so making sure that you know that we are referencing that chapter 2 this evening. Okay, let me go back over here. Go back to my PowerPoint, and we'll get started again. Okay. All right. So at the beginning here, it's this is our introduction. So in this chapter, we are going to be looking at how can we replace multiple forces with one force or one what we call a resultant. And we're going to find out when we talk about forces and when we represent forces, not only in statics, but in all of your courses going forward. Statics is going to be the basis for just about every problem you do in, well, strength of materials for sure, machine design elements, in dynamics. There's all elements of statics in those. So this really starts, if you would, kind of the, I'd like to call it the design part of the program. This is when you really start getting into understanding what's going on. And then we're also going to be looking at the relation between forces acting on a particle and their equilibrium. So that'll be something that we talk about a little bit later. So first of all, when we talk about a particle. Now, the only reason they use this verbiage in this book is because they don't want you to worry about how much does something weigh, what is the material it's made of. So they're kind of looking at it in terms of we're just looking at like a particle of something, not an entire body. Okay. So that's what this paragraph is about. It's not going to play too much of an element in it. It's just that it's just to let you know that we're not going to be talking about, is it made out of steel? We're not going to be talking about if it's made out of aluminum or what effect that has, because that's more strength of materials, which is a class after this. We're just going to be looking at things in a very generic sense and identifying and calculating forces. Now, resultant of two forces. So here we have a force. A force is going to be represented by a line with an arrowhead called a vector. I am confident that along the way, whether it's been a math class or it's been maybe a physics class or a science class, that you have seen forces representing in this manner, okay? We are going to be dealing with forces from today all the way through, okay? So again, it's going to be a line with an arrowhead. You cannot draw vectors without an arrowhead. Now that might seem like, well, yeah, I know, but you'd be surprised how many diagrams I get in, and I just have these lines that are sticking up, and then they've got labels on them, but they don't have any arrowheads. And it's important to have an arrowhead on a vector because a vector quantity, like a force, needs two things to fully define it. We need to know what its magnitude is. So the magnitude is going to be called out in two ways here. We have 10 pounds. Those are going to be the amount, the magnitude of that force with the units of measure that it's going to be in. And then you're going to notice that it's a certain length. So by representing that as a length, that is what we are designating as its magnitude, okay? And then it also has a line of action. So you're going to notice that this is going up and to the right. And then we see these dotted lines that are extending, up and to the right and down and to the left. That means that we can move that force anywhere along that line of action, and it will have the same net effect on whatever it is acting on, okay? And it just means that by that force, it's kind of either pulling it up and to the right, and that object or that particle is going to move up and to the right, or even if it's pushing on a particle, it's going to still go up and to the right. It's still going to have the same what we call net effect on the body. So that's line of action. And then lastly, you're going to notice that we have direction. Direction is going to be signified by two things here. It's going to be signified by the angle, 30 degrees, and the arrowhead. That's why we need the arrowhead, because if this is going up and to the right, it's very different than if it's going down and to the left. It's going to have a different effect. So if you forget to put an arrowhead on a vector, it's kind of like we're missing a part of the information that we need, okay? So vectors need two quantities to fully define the magnitude and direction, okay? Magnitude and direction. You guys ever watch Despicable Me? Was it the second one where Vector was the villain? Do you remember him? Do you remember when he introduced himself? I'm Vector. I have both magnitude and direction. Yeah, right? Okay, so you kind of get it. Like if you're a kid, probably when you're a little kid, you just don't really think about it. But when you're like in classes like this, or if you're somebody like me and I'm watching it, catching it with they're adult kids. We like Despicable Me the first time around. So you got to watch the second one. So when I saw that the second time, I'm like, oh, okay, I get it. That was pretty cool. So anyway, so vectors. Now, resultant of two forces. So if we look down here, inevitably, sometimes we have more than one force acting on, and I'm going to keep saying particle or a body, okay? So, or something. And in this case, you're going to notice that we have point A as our particle, all right? And there are two forces in this case. There is force Q and there's force P. Those are two, if you would, forces that are acting on particle A. Now, many times, instead of dealing with two forces, we want to figure out what is the one force that is going to have the same net effect on the body as those two separate forces. And that is called the resultant. Okay. So the resultant is, and they have it right here. The resultant is equivalent to the diagonal of what would be the, oh, I'm sorry. It's the first one. So experimental evidence shows that the combined effect of two forces may be represented by a resultant. So that resultant force is going to have the same net effect on, in this case, the two forces that are acting on point A. Now, we can solve for this resultant in a couple different ways. When we have two forces, there are two graphical methods that we can use. The first one is called the parallelogram method, as we see here. Okay. Now, what I'm going to do is I'm going to go underneath my camera and I'll show you this because I mean, it's one thing to look at it and point at it, but I want to show you how this actually comes about. So for instance, I am simply going to draw point A, and I'm going to go scooch a little further in. I hope you guys can see that. Okay. I don't know what that line is here. Okay. This is going to be my point A. And if we go back to our illustration, we have Q kind of going up and to the right. And I'm just going to draw this in a way that is going to, just kind of represent, because right now we don't know actual magnitudes and we don't know actual angles or directions. We're going to sketch this out for process. Okay. Now, I'm starting with an axis system. So kind of my standard XY axis. Okay. And then I'm going to just draw from that origin X. Okay. We're going to draw our vector Q. Okay. Right. Now, you'll notice here that for this vector, as I said, we've got a line with an arrowhead on it. The tail, what is called the tail, is at the origin that we have identified as point A here. So this is the tail of that vector. Okay. The arrowhead side is called the tip. Okay. So the tail is the non-arrowhead side, and the tip is going to be the arrowhead side. Okay. The other one that we have here is going to be force P, and I think it goes something like this. And again, we don't know its exact length because we don't have that, but its tail is going to start at the origin, and its tip is going to be where we have our arrowhead. Now, when you're sketching vectors for me, my expectation is you don't have to use a straight edge. I just do because I'm a little anal that way. But if you can draw a reasonably straight line without the use of a straight edge, and you can, add the arrowheads and the labels neatly, then you are in good shape with me. If you know you're not that good at that, then grab yourself a straight edge and it'll be better for you. Okay. Because remember, if I can't read or understand what you're handing into me, and that's really important, I can't give you points for it. All right. So just be aware of that. Okay. All right. So now I've got my two applied forces at A. So we want to find the resultant. We want to find the one force that is going to replace this and have the same net effect on the body. So to do that, we're going to use what we call the parallelogram rule. Okay. The parallelogram rule is going to be drawing a parallelogram. So we are going to take a line and we're going to draw a construction line that is going to be parallel to Q through the endpoint of P. So if my Q was like this, okay, and you could measure that angle and get it in there perfect, but I'm again going to eyeball this, but I'm going to use my straight edge. So something like this. I'm just going to draw a construction line out like this, okay, extending that out. And then through the endpoint of my other vector, I am going to draw a line parallel to its opposite. So if I'm going to go through the endpoint of Q, This is going to be a line that's going to be parallel to P. So do you see how we just drew, when we find that intersection, a parallelogram? Okay, that's why it's called the parallelogram graphical method. So graphical method is we're drawing this out. Okay. Now the resultant is going to start with its tail at the origin, just like the other two did. Okay, so its tail is going to start there, but its tip is going to go to that intersection that we just created with those two intersecting construction lines. Okay, and we're going to call this our resultant. I know those who are virtual, I'm going to tip this up a little bit so it's not the glare. Okay. Now, notice a couple of things. When I drew my vectors, each one of them has an arrowhead and each one of them is labeled, so I know exactly what they are. If I had more information about angles and such, in this case, we don't. We're just drawing the process of how to get a resultant using the parallelogram method. I would have then more information as far as like angles and such, okay? Now in this case, we don't know the magnitude of Q and P, we would need that to then actually get the number for our resultant. But if we had a scale, so if I drew this to scale and I said, oh, 1 inch is 100 pounds, I could figure out by each one of these measurements then what the actual magnitude would be, okay? You guys aren't going to have to do that, all right? I only want you to sketch the method so that you can see how to generate the graphical method, but then you'll be calculating the actual values using a couple different ways as we work through these problems, okay? Now, can you think of any other way that might give us, you know, if I would scale this and do it nice and accurate and use my protractor, that's a good graphical method, but can you think of any other way that I could draw this where I could get super accurate results? You guys have all had the class. Probably one of the first ones you took in the program. Probably the first one. Remember taking technical drafting? What did you learn in technical drafting? What was that? What was that CAD software? Go ahead.
You sketch, you make lot.
Do you remember the software that you guys use?
Yeah, AutoCAD.
AutoCAD, that's what I'm looking for. Yes, you can draw these in CAD as well. And then you're going to be getting results that are like spot on, like you would calculate, you know, to 13 decimal places. So if you wanted to, you could use that as also a very accurate way to graphically determine the results of, you know, the work that we're doing. But again, I just want you to sketch them and then you're going to be calculating the results using math that you guys already know. Okay, so that is the parallelogram method. And this is considered a graphical method to determine a resultant. And a resultant, as we know, is going to be the one force. So this R is the one force that would replace the two individual forces and have the same net effect on the body. Okay? Right. So that's what we see here. They're kind of going on. Oh, they're talking about vectors and scalar quantities. We already talked about vector quantities. We know that we need two things to fully define them, magnitude and direction. On the other hand, scalar quantities only need one thing to fully define them. So for instance, when we talk about things like mass, volume, temperature, speed, okay, speed, there's speed and there's velocity. If you've had this before, velocity is a vector quantity because the magnitude of that vector is going to be how fast you're going, the speed, but then it adds direction. So for instance, if you're in your car and you're looking down at your speedometer, the speed that you're going is what you're reading directly, okay? That's the scalar quantity. How fast am I going? But if you wanted to know how fast and in what direction, then it switches over to velocity. And some of you maybe had that through physics and things like that, okay? So even though we use the term speed and velocity interchangeably, one is a scalar quantity, speed, and the other is the added direction, which is velocity, okay? And then velocity becomes the vector quantity, okay? So that's all they're talking about here. Vectors, yep, we're looking at that. We saw the parallelogram rule. Let's look at the same type of process, but we're going to use the triangle method now. So using those same two vectors, Q and P, instead of using the parallelogram rule that we see here, we're going to use what we call the triangle rule. Okay, so if we go, or triangle method, I should say, not really the rule. So triangle method is going to be starting with our point A. Okay. And then what we're going to do is we're going to pick whichever force. There are two forces that are acting on point A. We can pick either point or vector Q or vector P. It doesn't matter. Whichever one we pick, it just happens to be the one that we're going to start with. So I'm going to start with, and I guess I'll draw my little axis system because I always do usually. Okay. I'm going to start with Q. Okay. And I'm going to start with the tail of Q at my point A, exactly where it's positioned. Okay, so this is Q, and I'm going to label next to it. Now, on the tip of Q, I am going to draw P. I'm not going to draw P back at point A, but I'm going to put it at the tip of Q. So the tail of P is going to go at the tip of Q. So I'm going to kind of go up here. I'm going to kind of eyeball this. I'm going to keep it at the same orientation, but then I'm going to draw it directly on the end point of Q, and this is going to be P. So it's still in its same orientation. If you were drawing this in CAD, you would literally move it from where it was originally, and you would move it to the tip of Q. The tail of P would go on the tip of Q. And then now, because those are the only two forces that are acting on this point, I'm going to now find my resultant by going back to the origin with the resultant's tail, and its tip is going to go to the tip of the last vector that was shown. So I'm going to try to show this way. There we go. And then you can see, kind of comparing my two here, you would get the very same result. You would get the very same result. All right. Either way, not one is better than the other. It would probably just be a preference at the moment, like which one you would want to do. Okay. So this is called the triangle method. And again, another graphical way of obtaining a resultant. Okay. How many have seen these before? Okay. If you haven't, that's okay. That's all right. But they're really just showing us graphically, visually, how to get that resultant. Okay. And again, resultant is that one force that's going to have the same net effect on the body. And when we look back up here at this one, where we have both P and Q acting through A, you can see that P is going up and to the right, and so is P, and so is Q. Okay. So when those two are going up and to the right, you would expect your resultant to also be going up and to the right. So always think of that. Think is my resultant making sense? Because sometimes something that students will just accidentally do is, instead of putting the arrowhead out here, because you are going along tip to tail, sometimes they'll mistakenly put the resultant with the tip going back to the origin. But remember, that resultant is always going to be the same net effect on the body as the two forces. And if these two forces are going up and to the right, then your resultant should be going up and to the right as well. Okay. If it's going down and to the left, then you're like, ooh, I must have put an arrowhead wrong somewhere. Okay. So always look at your final answer, no matter what it is. And in this case, kind of look, does it make sense, the direction that this resultant is going in? Okay. That I drew it. All right. Now, in this case, again, we don't have the angles. We would be adding and measuring for angles or figuring them out, because we would need both magnitude and direction. Okay. And so in this case, we could measure for that magnitude, and then we could also measure the angle. Again, CAD would give us a really nice result on this. Okay. So triangle method. Oh, the other thing that they're illustrating here too is whether you added Q plus P or P plus Q, as I said earlier, you're still going to end up with the very same resultant. Okay. And they're just showing it as P plus Q. Okay. One other thing, I'm just going to see if they do it here. Oh, they're showing it there. Okay. Then I'll wait a little bit. Now, you're going to notice that they're identifying the law of cosines here. As I said earlier, we are not going to be using the graphical methods with even scales and protractors. I'm just going to be drawing mine with straight edges because I like to. we are going to be finding our answers using mathematical methods. And the first two that we're going to be using are going to be the law of cosines, which will be familiar to us. If you want to write that down, you can. And this would be using this one, it would be using, in this case, it would be the resultant squared is going to be equal to one of the legs squared, in this case, P, plus Q squared, the other leg, and then minus 2 times each one of those legs, the length of the legs, and then the cosine of, now they're not showing us B, but B would be between the two legs of the triangle of the opposite of whatever side you're trying to find, if you remember that from math. We'll be using this a little bit later, so we'll revisit it again. The other thing that we see down here is we see this vector equation. I'm going to go underneath here. So if we look at, for instance, if, and I'm just going to give a value here. Let's say Q was 10 units long. I'm not even going to put units on it. I'm just going to be the value of 10, and P was the value of 20. As you look at this, is the length of the resultant going to be 30? No, why not? Because it's what type of a quantity? Starts with a V. It's a vector quantity, right? Remember, vectors have both magnitude and direction. We cannot algebraically add them together. We cannot algebraically add them together. So we can't say Q plus P is equal to our resultant unless they are along the same line of actions, meaning if they're all vertical, or they're all horizontal, or they're all along the same line of action. If it's at a different angle, then I can algebraically add them together based on their direction. So we'll maybe see that coming up, but we'll identify that then. But when they are vector quantities, we can't say 10 plus 20 is 30, right? So we have to write it differently. We have to write it and signify that it's a vector equation. So we would say Q plus P is equal to R. But we have to do one of two things in order to signify that it's a vector. We can, and this is the way I normally do it, I'll put a little vector above each one of the variables. And that's how you see it in our chapter on our slide. If I go back to here, resultant, and you see that there's a little vector right above the capital R there, that means it's a vector quantity. The same thing with the P and the Q. That just tells you can't add these algebraically. We've got to actually do a vector sum on this, okay? The other way that you may see it at times could be Q plus P, but then it has the greater than sign after the operator is equal to R. It's a little more subtle, but sometimes if you're, for instance, writing it out on a word processor or something like that, that's the way that you can get at that operator being not an algebraic addition, but a vector addition. So that's another way that you may see it. Okay. Then the other way, the other mathematical or trig way that is going to come in handy is going to be the law of sines. That's where we can take the side opposite it's the sine of its angle and set it up as a ratio and then find the unknown. So I'm sure you've used that along the way in your math classes as well. So that one we're going to find is going to be helpful at times. Okay. We talked about additions, vector additions. We talked about the equations here. We're not going to be worrying about vector subtraction in statics. You'll get to do it in kinematics. Okay, so we'll wait for that. Okay. The next section here is looking at resultant of several concurrent forces. So let's talk about concurrent first. This is the first time we're coming up with this term. So a concurrent force system just means that all the points or all the forces share a common point, whether that is extending to a common point or the point of application is there, okay, that they all are the same. So for instance, if I go back underneath here, Q and P are concurrent forces because they all share a common point A, okay? They all share a common point A. So if I go back here and I scooch up here a little bit. P, S, and Q, concurrent forces, they all share a common point A again. Okay, and they're all in the same plane, meaning they're in the X, Y, flat plane. There's not a Z variable that we're worried about. So a concurrent force system shares a same point. Okay. And what it says here is a set of concurrent forces applied on a particle may be replaced by a single resultant force. So in the examples that we saw earlier with the parallelogram method and the triangle method, we only had two forces that we wanted to find the resultant of. In this case, we have three forces. So let's see how we would do that. I have to kind of probably go back and forth a little bit. So I've got Q going down and to the right. I'm going to try to draw this. Start with my A. Okay, so here's my point A. So I know that Q is kind of going down and to the right. Again, they're not giving us much more than just proportionally what's there. So this would be my force Q. Okay, that would be my first one. Notice that I'm starting my first vector with its tail at, I'm going to call it the origin or the place where the application of the force is. And then its tail or its tip is going in the direction, in this case, down and to the right. Okay, and I'm labeling that vector. Now, the next force, now I've got two other forces. I've got P and I've got S. Now, if you would start with S or P, totally fine, okay? No matter what order that we add these vectors in, we will still end up with the same net effect or the same resultant. So I'm gonna pick S as my next one. So I'm gonna look, S is kind of going down and to the left here, slightly off of horizontal. So if I go back underneath here, I'm gonna go to the tip of my Q, and I am going to make S go back this way. So this is why I use pencil. I'm going to take my Q and I'm going to put it up like that. So now I took the tail of my S and I put it at the tip of the last vector. So I'm just doing these tip to tail, tip to tail. Okay. So then now the last one that I have here is P. P is now going to, its tail is going to start at the tip of S and it is going to actually cross over. That's okay. Don't worry about that. They can cross over. Sometimes do. So here's my P going up and to the right. Okay, this is P. So this would be the equation for these three forces would be Q plus S plus P, because I started at my origin with Q. That was my first one. S went at the endpoint of Q, and then P went to the endpoint, and I would put my vector symbol above each one of those. Now, this is a vector equation, so it needs an equal sign and a right side, okay? So equal to, it's going to be equal to the resultant. So I'm going to call it R is going to be my variable. I'm going to put my little arrowhead above. And now remember, I need my tail of my resultant to start at my origin, or in this case, point A, okay? And I always like to think of my equal sign as my origin, okay? When I cross over to the other side of the equal sign, I'm starting the tail of my first vector here back at that origin. And then its tip, this is why, again, I always do this. That's why I use pencil. Its tip, so its tail is going to start at the origin. Its tip is going to go to the tip of the last vector from the left-hand side. So here's going to be my R. And then to find its magnitude and direction, I would then measure two horizontal. So I would probably put my x-axis in here, my y-axis in here. I would measure the length and then come up with the angle as well. I would probably want to know what this is and then how long that would be. Okay. Now notice here that each one of these vectors has a tip and a tail. Every one of them has an arrowhead. Okay, and each one of them is labeled. Okay. All right. So questions on just the method and the process. Okay. Cool. Virtually, how you guys doing? Hopefully you're still there. I'm sure you are. Okay. Awesome. Good, good, good. Awesome. Good. Awesome. All right. Several forces. We looked here. Okay, we're going to go back. So let's do our first sample problem. This is going to be our first problem in our practice problem series. Okay. And this is sample problem 2.1 in our book. Okay. 2.1 in our book. So it says here, so what I'm going to do is I'm going to find where it is at. So it's on page 23 if you're following along in the textbook. It's on page, bless you. It's on page 23. And we'll read the problem statement first. Okay. So it says here, forces P and Q over on the left-hand side, they act on a bolt. We want to determine their resultants. So they kind of look familiar to some of those vectors we were looking at in our examples. But now what they have for us is not only do we have the length of the vector and which direction it's pointing in, but we now have labels for instance, for P is 40 newtons and Q is 60 newtons. And then we're given the angles that they're at. So we're given both magnitude and direction. Okay, so they want us to determine the resultant. So we're going to actually do it. We're going to do it. Oh, they're doing it three ways: parallelogram rule, or the parallelogram method, the triangle method, and we're going to do the cosine law to figure it out like math wise in the end. Okay, so let's do all three because we'll follow along with this example. Okay. So I'm gonna put this over here. First things first, I am gonna draw my two vectors, or I'm gonna first call this, I guess, sample problem 2.1. Okay. And we want to draw, they're using point A. Okay. We want to find the resultant, right? So this is going to be part A. Going to be point A. And I'm going to draw. Now, since for this first illustration, since we have point A and they're showing us exactly, see, P and Q in this orientation, we're going to do the parallelogram method first. Okay, so I'm just going to draw P and Q exactly as we see them here. And then we're going to do the parallel lines through the endpoints to do the parallelogram method first. So I'm going to grab this down here. So my P. Now here again, you would just be sketching the process. So if any of our homework problems, and we'll go over the homework problems once we get done with this stuff here, if any of them would say, determine the resultant graphically, then you would do sketches of each one of these. You don't have to draw it in AutoCAD or anything like that, but then you would follow up with the math. So kind of similar to what we're doing here, but you would pick one. So for instance, if it was in this case, you wouldn't do the parallelogram method and the triangle method and math. You would do either the parallelogram method or the triangle method. I think it's a good idea for you to see both, and then you can pick which one you want. So we're going to put our arrowheads on the ends. Okay, so by the parallelogram method, okay, which is this method right here, we are going to draw parallel lines through the endpoints of the vectors. So if I'm going through the endpoint of P, I'm going to draw a line parallel to Q. So it's always the opposite force. So I'm going to kind of line this up here. I'm just going to pull it over. And I'm going to draw a construction line or a dotted line. Of course, it's going to go up into there. Should have gone lower, but I'm trying to get this all on the same page. I'm going to go up something like that. Okay, I'll add in the 2.1 up here. Then I'm going to do that same thing through the endpoint of Q. So I've got P here. So through the endpoint of Q, I'm going to draw my construction line here. And I'm going to find where those two intersect. And that's going to be up at this point right there. Okay. Now I'm going to draw my resultant. Its tail is going to start at the origin at A. And its tip is going to go to the intersection that we just created. Okay. And we are going to label this R. That's our resultant. Okay. Now again, If we were using the graphical method as finding the magnitude and direction, we would actually measure the length, but we're not going to. Graphicals are only going to be for process, just so you know. All right. So that's the parallelogram method. Now, the other way they want us to also show the triangle method. Okay. So the next one is going to be the triangle method. So we're going to start with that point A again. I'm going to try to proportionally get it in the right spot this time. So this is going to be my point A. This will be my X. This will be point A, my Y. Okay. Yeah. And now from that illustration, okay, so we have our two forces here. We have to pick one or the other to start our triangle, okay? And whether you pick P or Q does not matter, quite honestly, okay? So I'm just going to go with P because it's the one that's a little bit lower here. So I'm going to go P. Okay. This is triangle method, okay? So I'll put that here. Right. So now on the tip of P, I'm going to start the tail of Q in its same orientation. So Q is something like, I guess in my illustration up there, try to go parallel. Something like that. I'm going to label Q. Okay. And then once I have exhausted all my forces, I am now going to start back at the origin and I'm going to draw my resultant to the tip of the last vector. And here's R. And because it creates a triangle, because I only have two forces that I need to find the resultant of, then I create a triangle. If it is more than two forces, then it's just going to be that tip to tail method, and I keep adding. Okay. Any questions on these two graphical methods, parallelogram method and triangle method? Okay. And again, for the problems that you end up doing for the practice problems, just like we're doing here, and for your homework, you won't have to scale these or use AutoCAD to try to find the numbers. You're just simply using it as a reference for labeling, showing the process, and then you'll actually get the numbers using the math that you know. Okay. All right. So that's the first two parts of this problem. The last part of this problem is determining the resultant. Okay. Now, remember the resultant is it needs both magnitude and direction. So we're going to be finding the magnitude first, and then we're going to also then determine its direction from the angle that would be 0. So we're going to use this triangle method right here, and we want to find what the length of our resultant is, and we also want to know what's its direction. And I'm putting the letter alpha here. So from our x-axis to the resultant, what is that value? So we'll work through that. Now, since we have a triangle here, okay, we know that P is equal to 40 newtons, okay, and that this angle right here is 20 degrees from horizontal, right? We also know that Q is equal to 60, oh, not 40 degrees. It's not 40 degrees, 40 newtons, 20 degrees, 40 newtons, 20 degrees for P, 60 newtons. And from horizontal, from where it would have been down at point A, this is 45 degrees because it's 20 plus 25. Okay. So 20 plus 25. So 45 from what would be like horizontal. Okay. All right. So now what we want to do is we want to try to find R. Now, if we look at this, are there any angles of this triangle, like internal angles that we can get? Yes, no?
Yeah.
Yeah, is there?
No.
I always like
To find the
this.
big one, find the obtuse angle, yeah.
This one right here. Yep.
Okay, yeah, you get 180 minus 45, you get about the top half of it, then you use. Then that at the point P, you make a right triangle, find the right triangle, find the degrees on that one. Then you use 20 degrees.
Well, I know where you're going. Okay.
Piece of paper. So
Yep.
I can show it. Wait.
I know. So I'll show you what I see. So here's my 180, right? Along here. This would be 180 full degrees all the way that way, right? I know that this is 20. That means that this angle right here is 20 degrees, right? And this one is the 25. So if this is 180 minus 25, what's left over here? Is it 155? Yeah, 155. So 180 minus 25. Do you see it? So 180. This one is 25. This one would be left over 155, right? So I'm going to call that beta equals 155 degrees. So that's your obtuse angle. Was that kind of where you were going with that?
Yeah.
Yeah. I like to do it that way because then I don't know, I see the 180 first and then I can kind of figure out this is 20 because that goes along there and then that's 25 left over. And then that would be subtracted from the 180. So we know this angle. We know the length of P. We know the length of Q. So we can use that cosine law, right? To get our resultant and then ultimately we'll be able to get the angle as well. So let me show you how to use the cosine law here. So our cosine law, okay, is going to be equal to, so when we look at the cosine law, I like to think of, we want to find, if we know our angle is 155, which is opposite the value that we want to find, okay? So in this case, we're going to start with resultant squared is going to be equal to one of the sides that makes up that angle. So I'm going to do P squared first, plus the other side, Q squared, minus 2 times P times Q times the cosine of, in this case, beta. Does that kind of sound familiar? You probably saw it in the form of C squared is equal to A squared plus B squared minus 2AB cosine theta. Do you remember that? Yeah. So in this form, the A and the B are the legs, the C is the hypotenuse, or I'm sorry, the resultant in my case, not a hypotenuse because it's not a right triangle. Okay. So now we're going to try to find R. So that's going to remain its variable. We know that P is 40. And make sure you put your newtons in there. In all phases of the problem, you need to put your units. That is a must in statics and pretty much all the classes you have with me. You get to do that. All right. We want to always make sure we end up with the right units. We're going to square that quantity. Plus 16 newtons squared minus 2 times 40 newtons times 60 newtons times cosine 155. So I'm going to try to sneak this in here, 155. Okay. And then if I put R over here, to solve for R because it's squared here, I would have to put the entire side under a radical. Do you see that? To solve for R because it's R squared on the left-hand side. Okay. So go ahead, plug it into your calculator and make sure that you can get the value. What is it? Oh, 97.7. So make sure you can get that with the numbers that we see here.
Sorry, did you say 97.7?
Yep, 97.73. Yeah. So if you look underneath, there's the resultant right there. You should get that number. 97.73. And that would be newtons, because everything underneath here would be newtons squared. And then we take the square root and it's going to be newtons. Now, since this is the magnitude of the resultant, we would put a box around that answer because that's one of them that it's asking for, okay? I'll let everybody get a chance. Make sure that you get that number. Kind of confirms doing it on your calculator, right? I didn't say this, but and it's I'm not saying it to say anything, but everybody can use whatever calculator you want, okay? And I don't know that they do this at WCTC, but the old school I was at, they would make everybody buy the same calculator and they would show people how to punch it in, okay? Which I think maybe at first, if you're brand new to it, it probably is easier for the instructor and all that kind of stuff. But inevitably, I don't know, I kind of like a certain type of calculator. I like how it works. So you can get whatever calculator you want. And the reason we work these problems like this too is so that you can confirm, like, do I put it in first or second, or do I, however you have to do your buttons on your calculator. That's the only question I can't really answer. All right. I use it's called an HP. It's reverse Polish notation is the type I like to use. It's like old people things to do. So yours is probably different. So when somebody says, did I put this in right? I'm not being rude. I'm like, I don't know. So that's why we do the problems that have the answers at the end of them too, so that you can confirm that when you put it in, you're getting the right answer and you know how to do it. Okay. All right. Did everybody get the 97.73-ish? Okay.
I got 97.2, but that probably just rounded.
Probably. Yes. And that's just kind of, I'm glad you brought that up as far as rounding. What you want to try to do is inside of the problem, hold as many decimal places as possible. So for instance, if you have a calculator that you can hold all those values in there, don't round them at all. Hold them to whatever your calculator is set to, just in your final answer. That way you'll always get closer numbers to what you're going to see as those final answers. And then too, just be reasonable. So if we're working with, 97.73, as long as you get 97.75, 72, 71, you're okay. But if you end up with 97.5, not close enough. Okay. Then you probably did round too much in the inside of the problem before you got there. So I always say hold 4, 5, 6 decimal places inside the problem and then just round your final answer. Okay. All right, so that's the magnitude. We're not done yet. We now have to find alpha, the angle to the horizontal that our resultant is going to be. So we can look here too, what we know about triangles. We know that the internal angles of a triangle are always going to be what? 180 degrees, right? Now, we know one of the angles, but we don't know these two, do we? We don't know. We're going to call this one, I guess we'll call this angle A. Okay, this will be angle A, and we'll call this one angle B, just to give it a variable. Does that make sense? So the two acute angles in here. Now, as we look at these, you'll notice that B is opposite to P. We know what P is, right? We know its magnitude. And we can see that A is opposite to Q. And then we can also see that the 155 is opposite to the resultant, which we just calculated, right? And we're solid on that number. So cosine law is out there, but is there another one that we could use possibly to solve for at least one of these unknown angles? Jesse, which one? The law of sines. Yeah. So the law of sines, those are I like to think of those as the opposites, right? Now, we're going to want to pick. Do we want to solve for A or B? We can't solve for both because in any of our equations, we can only have one unknown. So do we want to solve for angle A or do we want to solve for angle B? Any preferences? Anyone? How about virtually? You guys pick. Do we want to solve for A or do we want to solve for B? Watching. I'm sorry, Danny, what? Oh, B. Sure, let's solve for B. Really doesn't matter, okay? So we're going to solve for angle B, which is up here, all right? So if we're going to solve for angle B, we want to look, what is opposite angle B? It's length P, okay? So we're going to set this up, okay? Law of sines. And we're going to say, okay, the sine of B over P, which is 40 newtons. B is our unknown value, right? 40 is our P. So the side opposite is going to be equal to, and now we have to have our knowns. We know that the 155 is opposite the resultant, which is 97.73, which we just calculated. So we're going to put sine of 155 divided by 97.73 newtons. Notice we're putting our units in all phases of the problem. Okay, so our only unknown here is B, right? So we're going to multiply our 40 up on top. Okay, so we're going to multiply 40 newtons up here. Newtons will cancel top to bottom, right? And then you're going to end up with a decimal over on the right-hand side, which then you're going to take the inverse sine of to get the angle, right? Everybody agree? So go ahead and see what you get. So your decimal should be 0.173. And then you need to take your maybe second function sine or the whatever the inverse sine is on your calculator. And you should get B equal to 9.96 degrees. You guys get that same number? Right? Okay. Okay. So again, sine B would be equal to the decimal 0.173, and then you need to take the inverse sine to get the actual angle, right? So now if that's my angle up here, right? So I know this to be 9.96 degrees, right? So I know this angle, I know this angle. How can I find angle A? I know the total of the angles inside is equal to what? 180. So I can take 180 minus 155 minus 9.96 and I'll get A, right? So I'm going to turn this over. And angle A is going to be equal to 180 degrees minus 155 degrees minus 99.97 degrees. Angle A should come out to be 15.04 degrees. Yeah. Okay. Now, it's not our answer yet because that was our internal angle. Okay. Angle A. This is why we do, again, this is why we do pencil. This was 15.04. Okay. So that's this angle right here. I need from the x-axis to my resultant. So if this is 20 and this is 15.04, do you see how alpha is going to be equal to adding those two together, right? It's going to be angle A plus 20 degrees. Agreed? So if we do that here, alpha is going to be A plus 20 degrees. So 15.04 plus 20 degrees. Alpha is 35.04 degrees. Yep. And if we look at our final answer down here, our resultant is a magnitude of 97.7, which we had calculated earlier. And then its angle, because it did that same angle, 15.04 for A, is 35. They just rounded to 35 degrees. Okay, which is, we had 35.04. All right. Okay, so box around your final answer. labeled on your diagram. Here's my alpha labeled on my diagram. Box around your resultant. Your resultant is labeled on your diagram. Okay. So the things that I look for most here are going to be number one, all of your labels are on here. So I better see P's, Q's, R's. Okay. Additionally, don't make them super small. This is a little small for me. I think it came out okay, but if I would even take the top half of my paper and make it nice and big, because you're going to have to put in where are your P's and your alphas and your angles, so that as you're working through this, I can see what you did. So if you have, for instance, an R that you calculated for resultant, I better see R appear in your diagram. Okay. If you calculated for an alpha as an angle for your resultant, I better see alpha somewhere on your diagram. Does that make sense to everybody? Okay. This is so fun, isn't it? Jacob, I know you're just saying that. Actually, I don't know. I hope you enjoyed it as much as I do. I hope I said to you, this is number one, my favorite class to teach. And it's number two, my favorite class when I went through school. Like, I love statics. It's the best. This and GD&T, top two. So, all right. Okay, any questions on sample 2.1? That's our first practice problem. Okay. All right, very good. Where are we at? Okay, we're doing good. We're doing good. Let's go back to our PowerPoint presentation and kind of continue where we were at. We went through this, so this is just kind of talking you through what they did. We went through the very same thing. They just have a couple slides that they're doing it with. Let's look at another sample problem. Sample problem 2.2. Okay, sample problem 2.2. This is found right after, okay, on page 24. It says we have a barge is pulled with two tugboats. So the barge is the rectangular part right here. Two tugboats are up here, A and C. If the resultant of the forces exerted by the tugboats is 5,000 pounds directed along the axis of the barge. So the axis of the barge would be this horizontal line, like an x-axis going through B, okay? So 5,000 pounds directed along that axis, it's going to be going to the right. Determine the tension in each one of the ropes when alpha is 45 degrees. So you have one tugboat A going up and to the right at 30 degrees, and then alpha tugboat C going down and to the right at 45 degrees. Okay. So we're not going to discuss with our neighbor. We're going to jump right in because we got a couple things to do here. So I'm going to scooch down here. Now, just kind of looking strategy wise. So what they mean by there's a resultant force of 5,000 pounds that is going along the axis. When I zoom in here a little bit, okay, you can see here's point B, okay, on the barge. Here is point B on their illustration. We're going to be drawing this in just a little bit. I just want to make sure it makes sense what we're doing. We know that the tension in the cable to tugboat A is going to be along that line at 30 degrees from horizontal. So from point B, this is at a 30-degree horizontal, or 30 degrees from horizontal angle along that line, okay? We call that the tension because it's going to be pulling. It's going to be pulling apart. So they just call it what's the tension in the cable, all right? Tension is a force that's inside of that cable that's going to be pulling along the length of that cable. So they're representing the tension with a vector or a force, calling it T1. Okay. You could call it TA. The labels, you just have to label it something. Okay. So if it's not giving you a specific label, you could call it T1, you could call it TA, you could call it A if you wanted to. All right. But then once you label it, you want to be consistent in your work as you go. Then you're going to notice that there is another blue line going down and to the right. So this is at the 45 degrees. They said alpha was 45 degrees in the problem statement. So now you're going to notice that we have T2 going down and to the right at 45 degrees. Now, we don't know how long those are. We don't know how long those are, but we know that their resultant, the effect of those two combined directions is going to be along this horizontal line. And we know the magnitude of that force to be 5,000 pounds. That's how they have that drawn here. That's why we know that that line horizontally, 5,000 pounds. That's the resultant of those two pulling in the directions that they're pulling. Okay. So we're actually going to start with the resultant. And then we're going to draw these angles in either direction to find where they intersect so that we can draw then going backwards, if you would. But I wanted to make sure that you knew and saw what the different angles were here. So let's start with our illustration. We're going to start with point B. We're going to start with the 5,000 pounds, and we're going to draw that first on our paper. Okay. So I'm going to, again, take about the top half of my paper for this one. So this is going to be my x-axis. This is going to be point B. So this is my x-axis. I'm going to draw 5,000 pounds, just a length, okay? Remember, whenever we're drawing our illustrations, they are for that purpose. They're for illustration purposes only. We don't have to draw them perfectly. So this is going to be my 5,000, was it pounds? Yeah, 5,000 pounds. And this would be my resultant, if you would. This would be the resultant is equal to. Okay. Now, to go back along those lines, we know that, for instance, I could draw. So if you wanted to, if you were using your protractor, you would find, where is 45 degrees? 45 degrees from horizontal is right about there. And where's my little thing here? And through this, like along that construction line is where that T2 is going to be. Then I could do the same thing on top here. Might as well. I've got a protractor. This was 30 degrees, I think. Yep. So 30 degrees is there. Along this line, somewhere along this line, the tension T1 is going to be along there. Okay. Now, I know my endpoint. I identified the 5,000. Now, I just randomly picked this length. I didn't scale it out. I'm just kind of using it. But at this endpoint, then, I am going to draw a line parallel through here. All right. And then I'm going to draw a line parallel through here on that endpoint. Okay. And where I created those two intersections, this is going to be my T1. And this is going to be my T2. Now, if you drew the 5,000 to scale, you would be able to check that with the math that we do and see how close you were for T1 and T2. I should have done that. Okay, so you kind of see how it's developed here. If you would draw this in CAD and you would scale it to 5,000, let's say you would draw that, but let's say you would draw this 5 inches long rather than 5,000 inches long, 5 inches long. Then when you put these angles in here and you would find these intersections and do the, what do they call that? A line dimension on it. You got your answer, right? Yeah, so you can do that, but again, for our purposes only, we're just using these as sketches so you can see how it comes together. So any questions there right now? So then we want to add now our angles. We know this is 45 degrees. We know this is 30 degrees. And just for visualization purposes, we would know that this right here, right, is the same length as T1 as well. T1 is not located there, but it is going to be the same length. Do you see that right here? So if we would be looking at one of these triangles, right? We kind of see that relationship. Okay, so the question wants to know what T1 and T2 is, right? It wants to know what is the tension in each one of those. We know the angles that they're at. So when we look here, thoughts. We know the cosine law. We know this law of sines. Can we use either or both of those to get started here? We know that this is like T1, right? Okay. If we look along here, can you see that this is 30 degrees right here? I'm going to tip this up a little bit. Can you see that that's 30 degrees? So that means on the other side here, is this 30 degrees too? Yeah, right? This is 30 degrees. So then if I know that this is 45 and this is 30, can I calculate what this angle is? Yeah. So I know that this angle is going to be 180 minus 75, right? So that looks, I think that's 105. There we go. Okay, so we know all the internal angles. We know the resultant. Thoughts? Can we find one of T1 or T2 at this point? What would you use? Law of sine is where I'm kind of going, right? Because we know the resultant and we know the opposite angle. So that's a known ratio. We know an angle, I'm just pointing to the 30, but we don't know an opposite. That's only one unknown, right? Same thing in the other direction. So we can solve for one and then the other, right? So yes, law of sines is what I would go for here too. I agree. Okay, so let's do that. Law of sines. Okay. So what we know is, and we're going to try to find T1, T2. I'm going to do T2 with the 30 degrees. So that means I want my lengths of my vectors on the top, right? Then I don't have to do manipulating of the algebra. So I'm going to say 5,000 pounds. Make sure you put your units and you can use the pound symbol divided by sine of 105. It's going to be equal to T2. And I'm just putting the lengths on the top so that my unknown variable ends on top, divided by the sine of the angle that's opposite, which is 30 degrees. Okay. So multiplying sine 30 up on top, right? Dividing or multiplying on both sides, multiplying it up here. So my T2 is going to be 5,000 times sine of 30 divided by the sine of 105. I got T2. I get 2588.2. And that's going to be pounds. In the book, they round to 3 significant digits, 2590. I would do 2588. I don't know why I feel better about that. Okay. So this is one of my answers. Now, the reason we don't need the direction or the angles because it was given to us, right? We know that T2 is going down at 45 degrees. We just need to know the magnitude of T2, which is 2588 or 2590 pounds as stated in the problem. Okay, so that's T2. We got to find T1 now. How do we want to approach that one? Same thing? Absolutely, right? So I would take my 5,000 opposite the 105, and then we would take T1 opposite the 45. So go ahead and do that for T1. And you should get a magnitude of 3660. Okay. Okay. Now, there's one other part to this problem. It says, what is the minimum value of T2? I'm not worried about that. So don't worry about that. This is the way that it's set up. This is as far as we're going to go with that. Okay. So this is sample problem. This one was 2.2, I believe, right? Yeah, I didn't put that up here. So this is sample 2.2. All right. So as we look here, just as a review, make sure that you draw a diagram illustrating what the problem statement is, if you would. Make sure that you add all the labels, the angles, make it large enough so that you aren't, crunching it all together. Then you're going to, kind of orderly solve for the variables and put a box around your final answer. Okay. Make sure that you also put your units in all phases of the problem. Notice I have the symbol for pounds, in not only the final answer, but in the units or in the equation itself. If it would cancel out, I would be canceling it out and then making sure that I end up with the appropriate units. When I'm looking at tension here, tension is a force, so the units for force are going to be, in this case, pounds, right? Or in the last case, I think it was newtons that we were dealing with. Yes.
So if for homework, if we had a different way of getting the same answer and we just showed our work, would that be okay for homework?
What would be another way that you would do it?
I would turn the resultant into the XY. I would transfer the scalar to an XY Cartesian.
No. We'll do components in a little bit. So in this section of our book, please illustrate whatever they're working on in that section. So in this case, that we were practicing the sine and the cosine law, so kind of stick to those. When we get to rectangular components, which we will next, then we'll break it into X and Y components and go through that process. Yeah.
And during physics, that's how I solve these tests.
Mm-hmm. Other questions? All right. Okay, so then, since we're at about 7 o'clock, it's probably a good time to take a little bit of a break. So I'm going to stop our recording.